Here I have the derivative with respect to x of arcsin of x, or the inverse sine of x. What is it? And is the result we're going to derive obvious or not? And we're going to take a look at this through the language of implicit differentiation and our two favorite properties, the chain rule, okay, and the language of operators. And what I mean by the language of operators, I'm going to card the video right now on your screen, but operators are objects, mathematical objects that can act on both sides of an equation and input a function to output another function. And you can think of any function, almost pretty much any function, as an operator. For example, you can think of the natural log as an operator, and that becomes the process of logarithmic differentiation, or at least that's where it becomes very prevalent. And today we're going to look at trig functions as operators. So your favorite sines and cosines and tangents are all operators, I am excited to say. So let's look at the derivative with respect to x of arcsin of x. So I'm going to reproduce the equation right here so we can see it easier. And so what am I going to do? I'm going to start off with the same process that I always do. We're going to set y equal to arcsin of x. And writing this out like this visually is going to be really helpful for us, and you'll see why. So you want to show or find dy dx, essentially, and solve for dy dx. And now we're going to apply sine as an operator, which is going to be like this. I'm going to big capital S-I-N for sine. And so you get that x is equal to sine y. Okay? And it's essentially the same thing as inverting the two and getting x equals sine y as the alternate form for arcsine. And now we're going to differentiate with respect to y. But what we're going to do is we're going to look at this and differentiate with respect to x using the differentiation operator, d. Curly d with respect to x in this case is going to give us this. We get 1 because the derivative of x with respect to x is 1. And here we have the cosine of y, right? Cosine of y. And by the chain rule, we have to multiply this because y is a function of x here, arcsine of x. We have to multiply it by dy dx. And so what we get is that dy dx is equal to 1 over the cosine of y. Like this. And so we get secant of arcsine of x. And while this is an answer in terms of trigonometric functions, there's another way we can express this. And in fact, I have a video from a very long time ago on Josh Academy from near its genesis that describes the conversion of trig expressions into more algebraic forms. And that's what we're going to do right now. Remember that y equaling arcsine of x means that y is an angle, because arcsine x inputs a ratio of sides of a triangle, is one way you can think about it, and it outputs you an angle. So y is an angle. And so we can use right triangle trig to take advantage of these expressions and determine what they're equal to. So if we have y as an angle in our right triangle like this, then remember that since y is equal to arcsine of x, x is equal to sine of y. So when we get sine of y, we should get x, so opposite over hypotenuse. So if we set the opposite side to equal x and the hypotenuse to equal 1, then wouldn't you agree that sine of y is equal to x over 1, which is sine of x, which becomes just x? I would agree. Which means by Pythagorean theorem, we can fill out this left side, or the remaining side, which is going to be the root of 1 minus x squared. All right, and I encourage you to kind of understand the reasoning behind that. But we need to find the secant of arcsine of x, which is the secant of y. And that's not hard, because the secant becomes the hypotenuse over the adjacent. So we get officially that the derivative with respect to x of the function arcsine of x, the inverse sine, we get that it's equal to 1 over the square root of 1 minus x squared. And there you have it. That is the derivative of arcsine of x. And that looks very unusual. Why would the derivative be equal to 1 over root minus 1 minus x squared? And the reason behind that is that interpretation of the Pythagorean theorem connecting trigonometry and algebra. And that's another example of how important the Pythagorean theorem is in all of mathematics in general. So let's talk about the derivative of one of my other favorite functions, the derivative with respect to x of inverse tan, arctan of x. And if you're wondering why I like arctan of x so much, is because it's it pretty much is the only important trig function that is fully continuous on the domain of negative infinity to infinity. And arcsine, for example, doesn't have that property. It's a restricted domain. And same with arccosine. But arctan is much more smooth, and it's always increasing. It just has so many special properties. So, anyways, we're going to differentiate it. So, if we have y equal to arctan of x, then you know what we're going to do. We're going to take the tangent of both sides, which is the same thing as saying applying the tan operator. Okay? Acting on both sides of the inputs, equations, inputting functions and outputting functions. So this, we get x is equal to tan of y, right? And we know what tan of y is. We made a video on Josh Academy a little bit ago about the derivative of trig functions. So I encourage you to look at that, and that's carded on your screen right now. So we now take the derivative operator, the differential operator d sub x with respect to x. So differentiating x with respect to x, we get 1. And differentiating tangent, we get secant squared, right, of y. And we multiply that by dy dx by the chain rule. Okay? And ultimately, we get that the dy dx, or the derivative with respect to x of arctan of x, is going to equal cosine squared of arctan x. Okay? So I'm going to write that cosine squared of arctan of x. And we're going to do the same thing. We're going to use this idea of the arctan being an angle to our advantage. So if y is equal to arctan of x, then we can set up a right triangle with y in this corner here, or in the other corner, doesn't really matter. And since x is tan of y, then opposite over adjacent means we can set the adjacent side to 1 and opposite side to x, so that tan of y, right, is equal to x over 1, which is equal to x. So the remaining side is going to be root of 1 plus x squared by the Pythagorean theorem. And so when we take the cosine squared of arctan of x, what do we get? Well, the adjacent's 1, and the hypotenuse is root 1 plus x squared, but we square that. So we get 1 over 1 plus x squared. And ladies and gentlemen, that means that the derivative with respect to x of arctan of x is equal to 1 over 1 plus x squared. And that's very cool. That's a very nice expression. 1 over 1 plus x squared is not a very difficult function to understand or even graph. And I'll give you a brief kind of drawing of it here. It looks like this, sort of. And that's really cool, that when you sketch the derivative of arctan, you can also visualize that this is the case. Okay? So anyways, that's the derivative of arctangent of x. But there's another hidden truth within these inverse trig functions. So while we're using operators here, we can generalize this result. Because if you look at arctan, we have that when we have cosine squared of arctan of x, isn't that the same thing as saying 1 over secant squared? By any chance? Secant squared of arctan of x. I encourage you to convince yourself to see that this is true, that cosine squared of arctan of x is just 1 over secant squared of arctan of x. But what does that mean? We know that when we took the derivative of tangent here, we got secant squared of y, the inverse function. So maybe it's true that the derivative with respect to x of an inverse function of some sort, f inverse, is equal to 1, so the multiplicative inverse, if you will, of the derivative with respect to x of the original function, the inverse of the inverse, if you will, and evaluate this thing at the inverse function, like this. So the derivative of the inverse is the inverse of the derivative in a way, with words, loosely speaking. And it turns out that this property is true, and I encourage you to play around with the idea of using arctans and tans, and then also the arcsines and cosines with this expression here, and convince yourself just visually or algebraically by evaluating it that it's true. And this is provable if the function f is invertible, and as long as this bottom denominator isn't 0, because otherwise you'd be divided by 0, and you cannot do that, of course. So, if we have y equal to f inverse of x, and it's invertible, right? The function f is invertible, which means that it basically is 1 to 1, which means each output goes to one input and one input goes to one output, and it visually connotes the fact that the function does not fail the horizontal line test. So horizontal lines will only pass through one point at any moment. So if we have y equals f inverse of x, then as you know, using ideas of operators, we can take f, the function f, and use it as an operator to act on both sides of the equation. And f of f inverse of x annihilate each other, and we just get x is equal to f of y. And this is what we have when we use the technique of finding inverse functions by swapping the x's and y's. This is essentially what we're doing. We're applying the function f operator. And now, of course, what we're going to do, we're going to differentiate with respect to x on both sides. So we get derivative of x with respect to x is going to be 1, and that's equal to the derivative with respect to x of f of y, but y depends on x. So we get f prime of y, and you multiply that, of course, by dy dx. And so as you can see, that we get d dx of y, which is f inverse of x, and that's equal to the multiplicative inverse, so 1 over the derivative with respect to x of the regular function. This is f prime, so it's f of x, but we evaluate that at the inverse, at f inverse. And so we just proved that the inverse function rule for derivatives is true. So you could use that formula for computing certain derivatives, like inverse trig derivatives, or even logs and exponentials, and other inverse functions that you might know that are one-to-one, which means that, again, they do not fail the horizontal line test like this, right? An example is the cubic function, x cubed, and the cube root, which looks like this. All right, neither of those fails the horizontal line test, and that's why they are one-to-one and invertible. So anyways, I hope that this idea of the inverse function rule that we derived after observing certain patterns within the derivatives of trig functions, as an example, have given you another newfound appreciation or enhanced appreciation of not only the chain rule, but the language of operators. So remember, use your operators, use your derivatives, and there's more than one way to take a derivative. Till next time.